Okay, we're going to continue on here. It's chapter 10, which is energy. So last time we started talking about energy. And we talked about several types of units that are very common in energy, which is important to remember. Really common units are joules and kilojoules. Also, calories and kilocalories are oftentimes used a lot in terms of energy. The relationship between calories and joules is 1 calorie is 4.184 joules. So again, that's an important little conversion that we do use a lot here. When we talk about energy, there's really sort of 2 types of processes that we come across. One is sort of what is referred to as a exothermic process. And exothermic means that heat and energy is released. So whenever any sort of process overall sort of releases energy or gives it off, that's considered an exothermic process. There's really kind of 2 types of heat or energy type of formulas that we use to calculate things like that. Either Q, which is heat, and delta H, which is our enthalpy or change in enthalpy. These are 2 very common sort of values we use to calculate something like how much energy is sort of being released in a process. If either one of those values end up being a negative number, that usually indicates that what you have going on is an exothermic sort of process. Opposite of that is an endothermic process. And that is when heat and energy is absorbed. And once again here, if you look at Q or you look at delta E, those values will end up being positive values when you have some type of endothermic process basically going on. We talked about sort of energy diagrams as well, and a couple of parts of those. Remember that basically there's a couple of parts of it. We have our reactants going to our products. And whenever you look at, say, an energy diagram and you have reactants like we do in this particular case that are higher in energy than their products, in order for the reactants to get to the products, energy has to be given off. So this is always going to be a exothermic type of diagram. The opposite would be true where the reactants are lower in energy than the products. When you got something like that, that would be a endothermic sort of process. We talked about the idea of this sort of hill that we see in both of these diagrams, and the hill in both of these diagrams are what are referred to as the activation energy. And it is that is basically the energy hill that all the reactants have to climb basically to get to the other side. If I could draw a straight line, that would be a straight line across there. And it's the minimum amount of energy really required for a chemical reaction to occur. As we talked about last time, sort of the size of that hill really affects, how fast or how slow a reaction may take place. If you have a really large hill, then, it may take place a lot slower than somebody that has a smaller hill. That's really for a couple of reasons. It means that if you have a smaller hill, there's probably a greater amount of reactants that have enough energy to get up and over to the other side. So you obviously will probably see the reaction occur faster. Again, a larger hill, you probably have a lower proportion of molecules that really do possess that energy. Yeah. Taller. So this would be energy. I didn't draw here, but energy on the Y here. So as this hill gets taller, that means it's going to be more energy to get up and over to the other side. Yeah. Other questions? So just in comparison of these 2 that we drew here, this would be the activation energy right there. So again, you can see that one has a larger hill. Also, why we kind of talked about last time as well a little bit that That's why it's sort of endothermic, right? You got to kind of help it out a little bit, put some energy in there to help everybody kind of get up and over the hill to the other side. The difference in energy also between where the reactants start in energy and where the products end in energy is also what is known as the delta H of the reaction. So the difference between those two guys is the delta H of the reaction, or the enthalpy of the reaction. So here it would be, and that would be how we'd figure it out. And as I mentioned earlier, basically the way we calculate something like delta H of the reaction is to take our final state minus our initial state. So basically products minus reactants. So in the case of this one, which is exothermic, this value, if we went across, would be a smaller number than this value up here. So when we would subtract it, we would yield a negative value. As opposed to over here, if you just went across this way, the product number would be a larger number than the reactant number. So when you take products minus reactants, you'll get a positive value for your delta H on that side. Any questions on any of that stuff there we talked about? Okay, let's see here. So we talked about the idea as well that, heat flows from hot to cold. So if we did have sort of in a isolated container here, hot water on one side, cold water on the other side, basically the heat would transfer from the hot water to the cold water. And the process of that is we would see obviously the hot water start to increase in temperature. And eventually they would come to rest, probably halfway between the two temperatures if they were sort of in a nice isolated container where nothing's being lost to the outside. So let's talk a little bit more about enthalpy officially here. So most reactions are carried out under constant pressure conditions. And what that means is we'll actually do it in an experiment on Wednesday, I think. And you'll do it probably in some experiments in 1A as well. But you can actually very simply figure out sort of the energy of a reaction by using just something like some from cups and a calorimeter under constant pressure conditions. You can calculate the delta H. It is the, again, heat that's either released, absorbed during the chemical process. The change in enthalpy, which is the delta H, will give you that idea. As I mentioned before, the number in terms of determining whether or not something is exothermic or endothermic, the actual numerical value is not that important. It really is just a sign that you would be looking for to make that determination. The way that we calculate it is we could take the delta H of the products minus the delta H of the reactants. And to do that, there's a lot of times a table in the back of the book that has a bunch of delta H values. And so, for example, it may say N2 is 0 kilojoules, O2 is 0 kilojoules, maybe CO2 is minus 393.5 kilojoules, and so forth. Water is like minus 187.6 kilojoules. So there's actually a table that you can go and look up. And if you're given just a chemical equation, you basically look up all the values in this table for your products, and you basically add them to all the values, add them together, and then subtract it for all the values from your reactants. A couple of things that's really important if you do go to a table like this is you want to always make sure that you find what you're looking for, but you want to make sure that you find it in the correct state. So if it's a solid, a liquid, a gas, or something that's aqueous, they will have different values. So the most common one that people screw up on is like water, because you could find water in the liquid states, solid state, or gas state. People just go to the table, grab the first water that they see, and just sort of use it in the calculation. So always when you go to these type of tables, two things are really important. Find what you're looking for, and also find it in the correct state is the two things that you really do want to do it. Now, what we do is basically if we had an equation such as like 2a plus 3b goes to 4c. we would go to the table and we would do our products, and we actually would multiply the value that we would find for C by the coefficient. So we actually do multiply by the coefficient in the balanced equation. Then we would subtract it from the coefficient for A would be 2 for the delta H value of A plus 3 times the delta H value for B here. And that is how we would go about actually calculating. So when you're given just an equation, you're asked what is the delta H of this reaction, you would go to this table. You want to also always multiply by the coefficient times whatever value that you find in the table. Do all your products minus all your reactants, which again is that state function that we talked about, which is final minus initial sort of state. So why don't we try here for a couple? Let's see here. Just to see. Let's say we had this equation. We want to calculate the delta H for this guy. Let me write another one as well. We'll do, I'll give you the values here in just a second. And probably a little balance in here. So a couple of those. Perfect. All right, so some delta H values here that you would find from the table. H2, 0 kilojoules. O2, 0 kilojoules. All right, so take a couple minutes for each of those reactions. Calculate the delta H for the reaction by the coefficients, products minus reactants. Let's see what you come up with. I'll do it as well. Hopefully we'll get the same spot. Take a look. So again, in this situation, if you were asked to calculate delta H of the reaction, and pretty much all you were given was essentially the equation, you would do the delta H of the reaction is basically the delta H of all the products minus the delta H of the reactants. Once again, you would go to a table, obviously, and find all these values. The important part here is we're just going to very much add up all of our products and then subtract it from all of our reactants. We again this into account when we do that. So if we did our very first one up here, we'll do our first. So the delta H of the reaction here would be our product side, which in this case is the NH3. And there is a coefficient of 2 here. So we would take 2 times the value of NH3, which is right there, minus 46.3 kilojoules. That is pretty much all the products that we have. We then are going to subtract it from all the reactants that are added together. And in this case, we have one NH2, one N2, and the value of N2 is 0. So that makes it pretty easy. You really don't need the 1 there, but I'll put it there so you understand. Here is the 3 for the coefficient times the value of H2, which is also 0. And as you might see there, anything that is in its standard state, uncombined, like H2, O2, N2, a piece of metal by itself that's not combined with anything else, they all have basically delta H values of 0. So they're all kind of given a value of 0, which is why those guys are zeros. So if we do all that good stuff there for this reaction, we're basically just taking 2 times minus 46.3, Gives us a minus 92.6. First off, any question on that calculation there? Is this reaction endothermic or exothermic? It is exothermic. The delta H value here is negative, so we know that it is going to be exothermic. Any questions on that one? All right, we're going to do pretty much the same deal for the second one there. So for number 2, we're going to take our delta H of our reaction. Once again, we're going to take our products, which in this case is CO2. So 1 times coefficient there is 1. The value of CO2, which is minus 393.5. We're then going to add it to our other reactant, which is 2 times the value of water, which is in the liquid state at 187.6. And that pretty much takes care of all of the products. We're then going to subtract it from what we got going on the reactant side there. So on the reactant side, I'm just going to go underneath it. So I'm going to subtract and then write it underneath. For our CH4, there's 1 times the value of CH4, which is minus 74.6 kilojoules, plus 2 oxygens, each has 0 kilojoules. And that is pretty much all of our reactants. So if we do that, that's basically 393.5 plus negative, sorry, 393.5 plus 2 times negative 187.6 minus negative 74.6 basically gets us something like minus 694.1 kilojoules in this case. Any question on that one there? This one is also going to be exothermic. And we know that it is because that's pretty much what happens when you light a Bunsen burner, right? It's pretty exothermic, right? When you got all the gas and the heat coming off of it. In that question. Any questions on how to calculate delta H of a reaction if you're just given the equation and nothing else? So just given the equation, nothing else, you got to go to that table, find those values. They are sometimes referred to in the table as, these guys are sometimes referred to as a delta H of formation. So you'll sometimes see like delta H of F on the bottom for formation. And those are sometimes what the table values are sometimes referred to. Any questions on any of that there? Yeah. You would be given the table, yeah. So I know they want you to memorize a lot of things, but that's something you can't memorize. It's a big table. So you would obviously be given the values or the table and stuff like that. Other questions? Okay. All right, so that's what we saw last time. All right, so one easy way that we could kind of calculate the heat or the energy that's sort of taking place in a chemical reaction is to actually calculate what is sometimes referred to as the specific heat of a reaction. Now, the specific heat capacity is the amount of energy that's required basically to change the temperature of 1 gram of a substance by 1 degree Celsius. That is almost identical to the definition of a calorie, which step a calorie is to change 1 gram of water by 1 degree Celsius. There is a specific heat equation, which is what we see in the box there, is Q is equal to ms delta T. So there's a few variations you'll sometimes see with this equation. Personally, I use Q is equal to ms delta T. For the specific heat capacity, sometimes people will use SH. Sometimes people will use C for it as well. So you might see some variations for that particular guy there. So what are all these sort of values here? Q is the heat. And when we use this equation, Q is the heat, which is typically in units of joules or calories. M is the mass, which is in typical units of grams. S is the specific heat capacity. Which is in units of joules per gram per degree Celsius, are calories per gram per degree Celsius. And lastly, delta T is the change in temperature, which is final minus initial. And that's really important here is the temperature part of it. A couple of things. This is probably one of the very few formulas in chemistry where you actually do just leave the temperature in Celsius, degrees Celsius. So this is one of the ones where you don't convert to Kelvin. The reason for that is the specific heat capacity here is usually in degrees Celsius, unless you take physics, then they like to use Kelvin. But here in chemistry, we usually find them in tables with degrees Celsius. The other important thing is actually the calculation here. So Q here, as we talked about earlier, if you end up with a Q that is negative, or you end up with a Q that is positive, it will tell you if it's endothermic or exothermic. So once again, if the Q is negative, exothermic process. If Q is positive, endothermic. So S, which is our M, which is the mass, is always going to be a positive number. S, which is a specific heat capacity, will be positive as well. So really the only thing that will determine whether or not you end up with a negative value of Q is actually the change in temperature. So you always want to do final temperature minus initial temperature, because that may give you a positive number, may give you a negative number, and that will tell you if it is going to be exothermic or endothermic. So sometimes people are taught just, take the difference of the temperature, whatever it is, just take the positive value. But it's really important in chemistry that you do final minus initial, so that if you get a negative number, you understand that it is exothermic. And obviously, if you get a positive number, you'll understand that it is hopefully endothermic. So that's really important. Make sure that you always do it that way. That means in terms of temperature, right? If my final temperature is less than my initial temperature, right? That means that when I do my final temperature minus my initial temperature, energy has been released, right? So we're gonna get a negative number. And vice versa, if my final temperature was higher than my initial, when I do the difference in temperature, I'm going to end up with a positive value, and that will give me a positive amount for my heat. This is not negative, so that's just PowerPoint. The specific heat capacity of liquid water. So liquid water, you do need to know this number, 4.184 joules per gram per degree Celsius, or the calorie version, 1 calorie per gram per degree Celsius. So those are two values that you need to know. You also should be aware that that value, which is commonly used a lot, is for liquid water. So if it is some other state, it actually will have a different specific heat capacity. So for example, ice or steam, the specific heat capacity is about 2 or so rather than 4. So it does change depending on the state. But most of the time in reactions that we deal with them in aqueous solutions, which is basically water environment. So we oftentimes will use the specific heat of liquid water a lot. So definitely need to know both of those numbers. If I have a high specific heat capacity, does it take more or less energy to change the temperature of a substance? A high specific heat capacity takes more energy to change the temperature. That's basically what specific heat capacity is, the amount of energy required to change 1 gram of the substance by 1 degree Celsius. So if you have something like water, liquid water, which is a relatively high specific heat capacity, it takes a lot of energy to change 1 gram of water by just 1 degree Celsius. As opposed to if you have something that had a very small specific heat capacity, it doesn't take a lot of energy to actually change the temperature of that by a lot, by 1 degree Celsius. That's why everybody gets really nervous when the ocean water goes up by like, a half a degree or something like that. Because you think about how much water is in the ocean and how much energy is required just to change 1 gram of it by 1 degree Celsius. That's a lot of energy to just change that little bit amount, even though we look at it and go, doesn't seem like a lot. But if you put in perspective that it takes a lot of energy to actually just raise that much energy, that much of water by that little bit of a degree. You know, that's an important thing to think about. Any questions on that there? Yes, sir. There you go. All right. Except recently, it's been very hot outside, so I don't know if I want 100 of anything. All right. Yep. So we have specific heat equation. You definitely need to know the equation, and obviously the value for liquid water you do need to know. So here's a table of specific heat capacity, and like I mentioned before, that is the liquid version, which again is the one that you should know. And as I mentioned, as you can see, when you do change the state, it obviously does have some different values. So there could be some problems where maybe you're dealing with water, but it is ice or gas. You definitely want to use a specific heat capacity for it and for that. I would say water you should know. The other ones you don't need to know, memorize, but definitely water. They want you to know the two values there, the 4.184 and the 1 calorie per gram per degree Celsius for liquid water. That also, by the way, is the conversion factor that we saw earlier that go from joules to calories. So it's the same conversion basically, right? So if you remember the conversion, you'll know the specific heat capacity or vice versa. So that is 1 calorie is 4.184 joules. So it's the exact same conversion that we use. So again, in this case, it would take a lot less energy to sort of raise the temperature of these guys, as opposed to you see something like water, which has a pretty good specific heat capacity. All right, so why don't you try one here, determine the amount of energy that's required to raise the temperature of 10-gram sample of aluminum, specific heat capacity 0.89 from 25 to 58 degrees Celsius. Let's take a look here. So obviously we're dealing with specific heat, so we want to think about our equation, which is, again, Q is equal to MS delta T. In this case, we have the mass given to us, that's 10 grams. We also have the specific heat capacity given to us at 0.89 joules per gram per degree Celsius. We have our initial temperature, which is 25, and we have our final temperature, which is 58 degrees Celsius. So we really have everything that we need to plug it into that equation. The Q here would be our 10 grams and our specific heat 0.89 joules per gram per degree Celsius. Once again, we want to do final minus initial. So that's going to be 58 minus 25 degrees Celsius. In terms of units, the grams will cancel. The Celsius, when you multiply it, will also cancel. And that will leave you just joules left over when it's all said and done there. So we do a little 58 minus 25, gets us 33 times 0.89 times 10. Gives us a 293.7 joules. In terms of sig figs here, we did subtraction probably first, which means we should go to a whole number, which was 33. That's 2 sig figs when we multiply. That's 2 sig figs when we multiply. And that's 3 sig figs, right, when we multiply. So that means our answer really should end up right about there at 2 sig figs based on these numbers, which would then take us to 290 joules on the proper sig figs. Any questions on that there? We also wanted to convert it to calories. So once again, this is the conversion that you do need to know. So 1 calorie is our 4.184 joules. So if we use the sort of significant figure number there, we would divide by the 4.184 joules is a calorie, and that would get us we'll call it 69 calories. If you use the non-rounded number, you ended up with maybe about 70 or something like that. Yeah, something in that ballpark. Any questions on either of those there? All right. So again, in these type of processes here, you would just want to kind of keep track of kind of what you're doing mathematically, right? And kind of clean it up to the right sig figs at the end there. All right, let's take a look at another one here. By the way, with that endothermic or exothermic, that last one? That was an endothermic process. Heat and energy was absorbed. We got a positive Q, and we saw that with the temperature, right? The temperature actually increased. So that's why we saw an increase in temperature. So why don't we try this one? 294 joules of heat is transferred to 10-gram sample of silver at 25 degrees Celsius, what will be the final temperature of silver if the specific heat capacity for silver is 0.24? So take a couple of minutes to find the final temperature in degrees Celsius. Obviously dealing still with specific heat, so we're going to put our equation in there. We're going to take out what we got here. So 294 joules is actually the Q value. I know that because Q actually only has one unit. So it either will be joules or calories. The specific heat capacity is the one that has all three units, the joules, the grams, the degrees Celsius. So it's very common. Sometimes people kind of get those two backwards. Our mass here is going to be 10 grams. We have our initial temperature of 25 degrees Celsius, and we have our specific heat capacity of 0.24 joules per gram per degree Celsius. Slapping our numbers into our equation here, 294 joules is equal to our mass, which is 10 grams, times the specific heat capacity of 0.24 joules per gram per degree Celsius. Final temperature, which is enough. Try again. Our final temperature, which is what we're looking for, minus our initial, which was 25 degrees Celsius. So mathematically here, we want to solve this. So just so we're clear mathematically, you need to do some dividing first. Yeah, so we got to divide those guys to the other side mathematically. So that is 294 divided by 10 divided by 0.24. Going to get us a 122.5 will equal our final temperature minus 25 degrees Celsius. We then are going to add this, right, to the other side. And when we do that, plus 25 gives us a final temperature of 147.5 degrees Celsius. First off, any question on the calculation part? We're going to talk sig figs here in just a second, but any questions on the calc part? All right. So as we're doing this calculation, right, we do want to kind of keep track of everything. So obviously during this part where we divided, we should be looking at sig figs, right? And we should end up technically with 2 sig figs at that point, right? Which actually would take us to here. The next thing we did is actually add, which means we should look at decimal places, which means really we should go to a whole number, which means we really should end this guy about here at the whole number. And you get like a 148 degrees Celsius probably is the correct sig figs. Now, if you rounded here at this point, which you might not want to do in this case, since we're kind of continuing on with the calculation, but you do want to keep track of it, you technically would have ended up with 120 plus a 25, which gives you a $1.45 there. So again, you'll have that slight difference if you rounded kind of strictly. In my case here, I personally probably went around here to the end and kind of clean it up like I did, because it's all sort of one calculation. Yeah. Yeah, so you really should keep track of it as you go through. So clearly we're dividing here at this point. So we're looking at sig figs, which means technically if we were to end the answer at this point, it really should have been like 120 basically, right? Since we're kind of then continuing on with the process here, we would then want to maybe just keep track of where we should probably end up, which is about 120. And then we should add this to the other side. Now that we're adding, which is technically the last process that we're doing, we want to look at decimal places. And it's really this guy's going to determine the decimal places, right? Which is 0, which means now that we added it, we could just take it to the whole number there. We wouldn't be looking at sig figs at that point. It'd be the same thing if you did round at this point to 120 and then added the 25, you would end up with 145 versus 148. Other questions on that? Yeah. For me, I probably would be okay with it if you did it that way. Again, personally though, if I were to do this, like I said, I'd just keep rolling with the number on my calculator until the end and then kind of clean it up at the end. So if I would do it, I probably would end up with 148. But if I saw you got 145, I probably could figure out that's probably what was going on there. Yeah. But again, remember, you really kind of, if you're doing multiple sort of steps along the way, you do want to kind of avoid the rounding maybe to the very end. Yeah. But you do want to keep track of it. Other questions on that? So let's talk a little about heat transfer. And by the way, when we do these type of processes here, this type of experiment, that we see in these sort of problems can easily be done by actually just using like 2 coffee cups. Basically, they insulate really well, and you could do the reaction in the coffee cups. You could put a thermometer in there, which is what we're going to do on Wednesday, basically. And it works really, really well to do these type of experiments. And really, the only thing that you have to do in these type of experiments is basically follow the change in temperature. And since most things are done in some type of water environment, knowing the specific heat capacity of water, you can basically calculate how much heat is either being given off or absorbed in a reaction, which frankly 2 coffee cups basically will allow you to do that. Now, since there is a heat exchange that occurs when things are at different temperatures, let's just say we did an experiment like this where we had some water here that would say was at 25 degrees Celsius, just some water. And I take something that is like a piece of metal that's really hot. We'll say its initial temperature was 99 degrees Celsius. When I drop this piece of metal into the water, what happens in terms of metal? Is it releasing energy or would it be absorbing energy? It would be releasing energy. We know that because we would expect the metal to start to cool down, right? And as it's cooling down, that means the only way to do that is to release the energy. For the water, we would expect it to be endothermic and absorb all that energy that's being released by the metal. And what we would see for the water is the water's temperature would maybe increase, say to 28 degrees Celsius. Now, my piece of metal that went for a swim, what would its final temperature end up being in this example? It would actually end up being the exact same temperature as the water, right? Because it's sitting in the water, so it's coming to equilibrate with the same temperature as the water. So the piece of metal's final temperature in this type of experiment will also be basically the same as the water as it goes in for a swim. So this allows us to use really our specific heat equation to figure out things like, for example, maybe the final temperature of the water, or maybe the final temperature of the metal, maybe the specific heat capacity of a metal, by looking really at water's specific heat capacities equation. Because when we do an experiment like this, we could very easily know the mass of water that we're doing. We always know the specific heat of water, which is 4.184. And by using just a simple thermometer, like my picture on the right there, we could really just follow the change in temperature of water. So we'll know everything about water in this case that will allow us to figure out how much heat or energy that water gained or lost, right? And that's important then if we think about, say, our metal, for example, which we could use the same equation. So let's just say, for example, we knew the mass of the metal. We knew the change in temperature of the metal because we know how hot it was to begin with. We know it's going to be the same temperature as the water, right, when it's all said and done. We could use this to figure out something like the specific heat capacity of the metal, which would be Q of the metal divided by M delta T. So by doing an experiment like this, what we know is we already know this guy for the metal. We already know this guy. How do we get the Q of the metal? We could get the Q of the metal in this case from our water, because all the energy that the water picked up had to come from the metal. That means that the metal had to lose the exact same amount of energy. Remember that when we talk about energy, whatever amount of energy somebody loses should be the exact same amount of energy that somebody gains. So if we're able to very simply figure out how much energy that the water gained, because the only thing we dumped into that water was a piece of metal, we should know how much energy that the metal lost. The difference comes in the sign, right? So exothermic is a negative value, right? Endothermic is a positive value. So Q of the water will actually equal minus Q of, say, the metal. That means that if my water gained 500 joules of energy, my metal should have lost negative 500 joules of energy. The number stays exactly the same, except that the sign is different. One is negative for the exothermic guy, and obviously is positive for the endothermic. So this is a very common, very easy way. And it's actually what we're going to do on Wednesday during the lab is you're going to heat up some metal. You're going to figure out what the temperature of the really hot metal is. You're going to dump it in some water. You're going to follow the temperature change in the water. And you're going to be able to figure out the specific heat capacity of the metal that you heated up. And you can do this by really following the change in temperature of the water. Any questions on that there? It is important when you do that, for example, in this example, this guy will be a negative number when you do the change in temperature for the metal. Again, it's important that you do final minus initial, because if I had a metal that started at 99 degrees and then ended at 28, when I subtract those two, I end up with a negative number. Yeah, so the negative number from the change in temperature, the negative number from the energy for the metal will turn your specific heat capacity into a positive number, which is what it should be. So you want to always make sure, again, you're still doing final minus initial for the temperature, so all the signs work out right. Any questions on that there? All right, so why don't you give it a try here? 110 gram sample of a metal at 55 degrees Celsius raises the temperature of from 23 degrees to 25.5 degrees Celsius. Determine the specific heat of the metal. I'll put it up here, but you should know the density of water is 1 gram per milliliter. Yeah. All right, take a couple minutes. This is basically exactly what we described here. You should be able to figure out the energy that the water got and then use that information to figure out what is going on with the metal. Take a look at this one. So this is basically exactly what we were just kind of talking about. We basically have some water here, and for our water, we know several things about the water. We know there's 150 milliliters of the water. We know the initial temperature is 23 degrees Celsius. We also know the final temperature is 25.5 degrees Celsius. And obviously, we always know the specific heat capacity of liquid water, which is 4.184 joules per gram per degree Celsius. We also have, obviously, a piece of metal here that we know some information about the metal. We have the mass of the metal, which is 110 grams. We have the initial temperature of the metal, which is 55.5 degrees Celsius. We also are looking for the specific heat capacity of the metal. And the one thing we know is when this metal goes for a swim, it will eventually come to rest at the same temperature as the water. So we also know the final temperature here of the water, which will be the exact, the metal, which will be the exact as the water in this case. Any questions on that there? So if we think about what we could really use our specific heat equation for here, our Q is equal to ms delta T for our water. We pretty much have everything that we need. We do need to convert technically the density of water, the volume of water into grams. So that is 1 gram per milliliter. That means that we really have 150 grams of water. So we can use the density of water to convert our volume into mass, so we have the right units. So putting that in will give us 150 grams. Our specific heat of water, 4.184 joules per gram per degree Celsius. Once again, we're going to do our final temperature, which is 25.5 minus 23 degrees Celsius in this case. That is going to get us, for our water, 150 times 4.184 times 25.5 minus 23, going to get us a 1569 joules. If we're looking at sig figs at this point, we got 4 sig figs. We got 4 sig figs. And when we do the subtraction here, that is 2.5, which is actually 2 sig figs in this case, which means really this guy should probably end up somewhere at 1600 joules at that point. Any questions on that there? That is the energy that was basically absorbed by the water, right? and that's why we see it is a positive value for the water. It's endothermic for the water, picking up all that energy. That number is really important because that also then tells us in terms of the metal, how much energy was released, right? And for the metal, Q of the water will equal minus Q of the metal, which means the Q of the metal in this case would be negative 1600 joules, which also makes sense because it's negative exothermic for the metal. It's giving off that energy, and it's the exact same amount of energy that was absorbed by the water, should be the exact same amount of energy that was lost by the metal. Any questions on that? That's important because that's really the missing piece that we needed for our calculation for the metal. And if we do our calculation for the metal here, Q of the metal would be MS delta T. Solving for the specific heat capacity would be Q of the metal divided by M delta T. We now have the Q of the metal at minus 1600 joules divided by the mass of the metal, which was 110. Divided by the change in temperature, which once again, we want to do final minus initial. So final is 25.5 minus initial 55.5 degrees Celsius. And if we do all that good stuff there, gets us a specific heat capacity for the metal that should be a positive 0.48 joules per gram per degree Celsius, as none of these units cancel. They all stay. Yeah. Yes. That we did, which was for the water. That basically. And really the only thing here that would change the temperature of the water was this hot piece of metal that basically went for a swim. So all the energy had to come from the metal. And there's sort of a perfect exchange of energy that we talked about. So if the water was able to absorb 1600 worth of energy, that means that the metal had to be the one releasing the 1600. And that's basically denoted by the negative sign here. The value again would be. Other questions on that? All right. Questions on this? This is again very common sort of procedure and exactly the experiment we're going to do on Wednesday. You're going to, like I said, take a bunch of metal, heat it up to a really high temperature, and then you're going to dump it into some temperature, some room temperature water and some coffee cups, and follow the temperature change. Any questions on specific heat here? Okay, I think we'll probably lay it up there for today.